Hi there, welcome. Today's another video update on the Hypermesh lattice measure. Let's jump into it. So what you see here is the Git graph again, and so the last few days I worked on a feature, which maybe I can best show that in the issues. I think I've closed that one. No, it's still open and it's not done yet, to be fair, but well, the goal was to just having a method how to import Hyperview data or result data of OptiStruct to be precise, and then assign them those values to the elements and use that for scaling material properties. So it's a big issue here, but I've made a little progress, and I think there's not a particular issue for that. No. All right. Let's walk through with the code here. So what I did was I implemented a reading method of reading stress and displacement outputs from a Hyperview reading TCL script thing and exporting that on a text file. So it's now ready for use to create the text file, and I will show that to you how this works, and then also cover the next steps, which are due on this project. All right, so what did I do? You see here that first of all I changed the data structure. So what really bothered me was that data and algorithms were not separated in separate folders. So we had this export folder, but in this export folder we had also the classes which are concerned with exporting files, as well as the data which is exported. So I don't want that. I restructured it like this, that we have in the Hypermesh lattice measure directory, I have now data, and data contains only this data. Export, import, and test. Test is not really used yet, but you could imagine that maybe I will create tests which include files which are not mocked, but really are files and executed on them and whatever. And that's what the test folder is for, but it's not used currently. But export and import, those are the values or the folders which we are using right now for data input output. All right, so. And then I think the best way to show you what is new is the main file. So in the main file, you have the commands which you can execute via the CLI, command line interface. So read displacement and read stress is the new methods on the block. So we had mesh FEM file and we had mesh, right? So going back, mesh means putting a TCL command line together, executing that on a FEM file, taking the 3D elements, making a lattice mesh out of it, outputting that as a FEM file, meaning starting Hypermesh, executing all the TCL commands, and then you're getting the Hypermesh file. And mesh FEM file, that's a direct way of doing the same as above, but with, directly in the FEM file, which is so much cooler and so much faster. I really can't believe that it took me this long to get to this. So the new methods, read stress. So let's say we have a model which we have executed with 1D elements. So it's a lattice mesh model, similar to, let me show that to you. Wait a second, I can move my Hypermesh over here. So similar to this one. Actually, this is what I was using for testing purposes. But you see now here is just a lattice mesh, and you have the constraints on one side, and on the other side you have some forces which are acting, and those are put into a load step, and yeah, you get OptiStruct solver, and now you have values. Values you have, what do I mean by that? We have data export Hypermesh, and here's your Hypermesh FEM file, your H3D file, which has the results in it and can be used with a Hyperview TCL command script file to extract the solver output values. For example, displacement or stress. In this case, it's stress. So what does it do here? A bunch of paths, and now we have a new method here, script builder Hyperview. Well, this was there, but it was not used in the main method. And you have this method here, write TCL read rod stress. This is one method, and the other one is completely the same, but it has write TCL, read no displacements. Actually, when thinking about it, maybe we should combine those two together and just put in an enumeration, for example, to differentiate between displacement and stress. But right now it's separate methods. All right, so read stress executes this write TCL read rod stress method. And what this does, it puts together a TCL file, which consists of this commands. It loads in a Hyperview file, and it creates some reference paths like output path and stuff like that. Imports the model, and then it goes to here, set data type element stresses 1D. So this is setting it to 1D stresses, creating an element set, adding all the elements which are there, putting it out, query, write it out to the out path, and that's it. So you see, we have export, and then I think a values is the stuff here, but it seems like it's not filled with values. All right, then let's just execute this for once. I have to see, it's really not, I have not cleaned that up until now, but I have already and all the time I have this content environment, and it's a little bit pissing me off, but yeah. We can do something like this, poetry shell, and then we are in a poetry environment, and this is, yeah, you can see it also here with poetry, and this makes sure that we have the poetry dependencies loaded and stuff. I hate that content environment, to be honest right now, but I have to clear that up ultimately. But now we have the poetry environment, and we can now execute. For example, Python -m for module, and then it's the Hypermesh Lattice measure.main, and now the command which we want to use, I think we want to use reads. Oh, not here, here. Read stress. And I programmed it like this. When you don't give any path, it takes you to the standard model path, which I have right now for testing purposes. It's just a lot easier to do that. And I misspelled Python. Shame on me. All right, and now it's executing this. And what you can see also here, it's with export scripts, you can see here model name. Well, maybe I should rename that to a little bit different. But this is right now the script which is executed. And I cannot believe my eyes. Why is it like this? This should not be here. Let's see if there was if I didn't correct that, because I think I had. So read stress, this is what we were doing, and then write TCL, blah, blah, blah. And then we have, oh, current simulation. All right, never mind, it's all right. It's all good. So I thought this was something different. Let me see, model name. Yeah, that's okay. So the data type thing, I renamed that to element stresses, and instead of picking the last element or the last data type, I should say. So it's all right, but there are a few spaces. I don't know why. Maybe you should correct that too, but it's working, or I think it is. So you have finished Hyperview run, and now you can see with values, there should be something like output text, and there you see those are the element values, right? So this is the axial stress in this case MPa. For each element ID you have the value, right? So this works for just fine. And the same thing goes with read displacement. And again, I'm just using the default model for this, and this is the default model is here, Hypermesh and model1.h3d, which you could also see here. If it equals empty, then it will be set to this. Yeah, it's just a bit of a easy way to test it. So finished Hyperview run, so this works, and now we can look again in the output text. It should be different values. Yeah, you see much less entries. And now this is all good, and I think it's a proper functionality added to it, and also it's maybe interesting for you to check out the TCL scripting, because you see how Hyperview scripting is done here on the model, really on the practice. But Besides that, it's just the first step. Because the next step, what I think would be cool right now, is just imagine that we now have the element stress values, or we do have the displacement values, whatever we choose to use as a metric. We will be using that with the elements. And just imagine that you have now your lattice mesh.fem file. You have that file, and now you want to change material parameters in order to do your own little optimization, your lattice optimization you could do. And for that reason, we need a method to properly assign new material data to each and every element. So this is the goal. And I think the easiest way to do it is to just scale the diameter, because yeah, why not? So diameter is super easy. Well, actually, you could also choose to change the Young's module, for example. I think it's as easy as. But the thing is, with the diameter, you could set the value of the diameter to exact value. And with the material, with the Young's module, I don't know. Well, you have to scale it either way. But let's back up a little. So what I think would be cool is having a method which gives every element its new material data based on the values you see here. You saw here, for example. So this could be it. This could be it. So you have this data, or the stress data, and you're scaling now the element data of each and every element. So this for sure has its own logic, how to do this. But the thing which I think is pretty interesting right now is that there are two ways of really doing it. You could do a calculation of new material data and then assigning for each and every element a own property material data, right? So every element gets its own property, its own material, and its own value. You will be ending up with duplicates, maybe, but maybe not. But in reality, I think you do. So what better approach could there be? Let's say you just create a bunch of baskets, like from, let's say, if you have the Young's module, you could say you go from 1,000 to 500,000 in thousands of steps, for example. And then you have your baskets or bins, right? And you put each element, depending on where it is on the spectrum of your stress values, you're putting it into the corresponding bin or basket of your material data. I think that would be a great idea, because then you have a finite set of material bins or baskets. Maybe not every one is filled, but if you have large models with large number of elements, this will cause you a significant speed up. But I think it's not so easy to do this straightforward. Not sure why, but let's imagine we are doing that. We have the baskets, we're putting that into, well, the thing is, can we do that directly in the FEM file? Or should we use TCL commands? How much of a speed thing is there? Because we saw with the meshing process, it took quite a while. And let's say we want to loop and do that multiple times to change the material properties. How would the process like this look like? So there are a bunch of questions which are not really answered right now for myself too. But I will start with something simple. So that's just that you know in which direction this is headed. I think the next step will be creating, taking a FEM file with a lattice mesh, importing that, deleting all the properties, creating a bunch of baskets, like with different material properties. So for example, let's say with the diameter from 0.01 millimeter to 2 millimeters in 0.01 millimeter steps. You create just a bunch of properties with different diameters, and you create that, and then you write that as a FEM file out, and then you have the sorting method where you can just give a dictionary, for example, where you have each and every element ID and the basket it should belong to, and then you have the sorting method where every element is put into the right property. I should say the right property is found, assigned to the element, and so on. I think I will start with a TCL script loop. And if we see that it is easier to do that directly in the FEM file, so we can directly measure the speed up we are getting from this. I think it's possible, but I think it's not that straightforward. But yeah, this is just my 2 cents on that. And I will see what comes up in mind. And if that's properly implemented, let's just talk way ahead in the future. If that's properly implemented, we can take or think about our own strategies, how to look what the density values should be, or the material data values. But I think this is also a major point of the students I'm supervising. So they have to come up with some ideas on that. But yeah, I'm curious on how this will work out. So enough talk for today. That was it for this video. I hope you learned a bit, find it interesting. Thanks for watching. If you have any questions, comments, please let me know down below. And yeah, see you next time. Thanks for watching. Bye guys.